All right, let's go over our last assignment in Unit 10 before you get to the Unit 9 and 10 review. So we are wrapping it up here. Okay, our first one, create a 90% confidence interval for that slope of the relationship between size of homes in square feet in Ithaca, New York, and the assessed value of those homes. Okay, so we are going to do a complete panic. So beta is the slope of the relationship between the size of the homes and its assessed value in Ithaca, New York. Now the assumptions is R line, R for random. So stated that we had a random sample of 18 Ithaca, New York homes. So our sample size was 18, degrees of freedom 16. Now, L for linearity. So here was the graphs. Let's take a look at these graphs real quick. So graph A is the X size in square feet and then the assessed value, so XY. So it's the XY graph. So that's going to be for my linearity. Graph B, oh, I can see this is one, look at that. Does that say percent score? Oh, normal score. That says normal score. Okay, that's like a Z score. And then the residuals, okay. So this is going to be how, look at there, 68% of my data is within one standard deviation of predicted, and then 95% is within two standard deviations, and so on. See, and then it's kind of this straight line here, more dense from -1 to +1. Okay, so that graph B is going to show me that my residuals are approximately normally distributed. And graph C, let's see. This one, here's my LSRL. That's a residual plot. And look, I can see that the whole domain has equal variation in those residuals across that whole domain of X. And it is not changing based on X. It's not fanning out or anything. Okay, so let's do that. Here we go. L for linearity. Graph A shows that a linear pattern, and R of 0.57 shows a moderately strong linear correlation between square feet and assessed value. Independent, so I'm assuming that these Ithaca, New York homes are independent of each other. So each one is its own separate single home. In normal probability plot, graph B shows that the residuals are approximately normally distributed. And E, equal variance in the residuals. Graph C shows that the residuals are equally varied on either side of this LSRL and are not affected by X, do not change throughout the domain. So in conclusion, the linear model applies. It's a linear regression T interval, so I'm going to go and compute this. So remember this formula for confidence interval. My sample slope plus or minus the critical value times the standard deviation of the slope. Of course, sample slope is up in the computer printout. Standard deviation of the slope up in the computer printout. But this critical value here, I do have to put some thought into. It is not a t-score given to me right here. Okay, so it is based on how confident? 90% confident. Okay, so we were going to be 90% confident. So my critical value, if I have 90% in the middle, then I'm going to have 0.05 in a tail. So inverse T, one tail with 16 degrees of freedom, negative 1.75. So my critical value is that plus and minus 1.75. So I am 90% confident that the slope of the relationship between square footage and assessed value of the Ithaca, New York homes is between $4.39 and $19.41 per square foot. Okay, that pretty much sounded ridiculously low for me. So I wondered if it was supposed to be in tens of dollars or something, and it was actually supposed to be 43.9 to $194.1. It may be even in thousands. I don't know what, but I'm pretty gosh darn sure it's not 4.39 to 19.41. So that came out strange. When you are writing your interval, don't forget to write down which degrees of freedom you used for your computing. All right, so that was the free response problem. Practicing R line, the um, the assumptions. Okie dokie, here we go. So here we had a printer that failed and did not write out the p-value. The hypothesis was 0 for the null hypothesis and beta is not equal to. So this right here is telling me that it is two-tailed. So here is a problem where you are being asked to compute with this t-score. So I am going to TCDF from 8.61 out to 99 with 4 degrees of freedom. And that gives me this value right here, which is A. So answer choice A is the p-value for one tail. But because this is two tails, I need to multiply that by 2. So when I multiply it by 2, I get 0.001, which is answer choice B. So right there, you had a problem where if you did not compute the tails properly and get both tails, then you got the wrong answer. Alrighty then, here was filling in this 95% confidence interval. 95% confidence with 12 pieces of data. Right here makes 10 degrees of freedom. So my critical value is really a major component to helping me do this one. Inverse T of one tail, 0.025 is in a tail with 10 degrees of freedom. So there we have our 2.28 critical value, and then you see the other ones plugged in correctly. All right, number 4. Assuming the conditions have been met, which the following conclusions is appropriate based on the above data. So I see that the p-value is low. So I would reject the null hypothesis and say that there is evidence of a linear relationship. Okay, so there's evidence of a linear relationship. And then because these problems down here, so I wanted to see there is evidence of a linear relationship. So no here, no here. There is evidence. Okay, so that one is evidence. And then this one, oh, not enough information. No, that's not true. Okay, so I'm actually down to either C or D at this point. But I see that the other language this is asking me about is the variation in the size of the house related to the linear relationship. Most of the variation is that there shows a significant relationship between the size of the house and the year. So it's talking about the variation in that y can be explained by the linear relationship with x. So I know in my vocabulary of statistics words that it's that r squared that talks about the percent of variation that is found in the y. So that's 95 points. So that's most of the variation in the house, the y, can be explained by the linear relationship with the year. So that is then how I knew the answer choice was C, 95.6% of the variation in the size of the house, not what D says, which is little variation. All right, and here we go. Ooh, this was an interesting one. This one is a big throwback. I kind of threw in a review problem for everybody. So here, we actually just used some normal model math, and it said the chocolate bar production the bars are independent of each other. Okay, the weights are approximately normally distributed, so use the normal model math. And so what we find is what's the probability? So what's the probability that 2 bars will weigh less than 7.5 ounces? So what I first did is I said, oh, the mean is 8. Well, let's find the probability that one bar is less than 7.5 ounces. So that's what I did first. I just did like chapter 6 from October. I did normal model math where I'd get my z-score, x minus the mean over the standard deviation, and then I norm CDF'd that lower area. And so that gave me that there. Once I got this probability here, I need 2 chocolate bars. So that's this one, and they're independent of each other. So I need this one to be less than 7.5 ounces, and I need this one to be less than 7.5 ounces. So those numbers just multiplied together. So that was A. All right, and then our last one here is our trio. Here we had a chi-squared problem. Chi-squared test was performed, so that one was D. You can see my answers there. Number 2, randomization of the treatments. When you need to spread unknown traits evenly, randomize. Randomize. When you need to spread unknown traits evenly, randomize. So it was making roughly equivalent groups. And the last one here, oh, this was interesting. So when I have a problem like this, I like to put the line y equals x, because if I do that, if I have a lot of data above the line, if most of my data is above the line, then the y's are higher values than the x's. On the lines, the y equals the x's. So I can see that most of the data is above the line, so the instructor's rating is generally higher than the course's rating. Okay, so that's how I do that, and I can tell that on there. All right, that's the end of that, going over those homeworks. So I hope that helped you, and I hope that you're doing well on those review problems as well.